Yeah, so I would like to thank my colleagues to organize this nice meeting, and I will talk about the model space of quadratic differentials, Abel-Jacobi maps, and deformation. So I will sit down because I twisted my ankle last month to save some energy. Yeah, so this is my plan. So first I will review the various model space of quadratic differentials that I will study. And secondly, I will talk about the categorification of these spaces. This is basically from representation theory of algebra point of view. And the third part is the main result is that we know how to calculate the fundamental groups of these spaces. And finally, I will draw many pictures to give you an idea of the proof. So first, let's recall the model space. So first, I will use numerical data to describe this model space by fixing prescribed singularities. So such a model space consists of a quadratic differential on a genus G Riemann surface. So that is a section of the square of cotangent bundle. And then we allow singularities, so it is meromorphic, and we divide the singularities into two types. The first is finite singularities, consists of zeros, normal points, but special as special marking, and then the simple pole, because for those singularities, there's a metric, and when you go there, there is a finite distance. And then the other type is infinite critical points, consists of poles of order at least 2. So locally, you can just think of this quadratic differential is given by something like that. I mean, maybe there are higher terms. So for example, if for the genus 0 case, we can take a polynomial, say without double zero, then you can globally write down this quadratic differential on CP1, where it will consist of, say, n plus 1 simple 0, and at infinity, you will have this n plus 5 order pole. So another example is that you can take some polynomial divided by another polynomial, and this will still on CP1, so the genus 0 Riemann surface, and say maybe with 4 simple 0, 2 double pole, and 1 order 4 pole at infinity. So that's kind of the model space we would like to study. So the key property of quadratic differential is this foliation structure. And basically, this is pulling back the horizontal foliation from C, which is defined by the imaginary part of the complex number to be a constant. So on the left-hand side, we have the foliation structure around this is simple 0, so order 1, 0, and then this is normal point, and this is a simple pole. So you can see the pattern is that you just glue many copies of upper half plane at origin. So this is finite singularity. And on the right-hand side, you have the behavior of foliation at higher order pole. So this is order 3 pole, and this is 4, this is 5. And you can see the pattern is that you are gluing upper half a plane at infinity and take some copy. So the number is usually the order -2, and -2 because we are considering quadratic. And in the middle, this is the things could happen at a double pole, which is most complicated. So usually at a generic point, you should have this logarithm spiral. But you can also have this co-centered circle, or you can have straight line through these points. And then let's give another description of the moduli space, because after all, it's on surface. So let's use some topology. So basically, I will use this weighted decorated marked surface with puncture to record all the information we have. So there are many terminologies because each of which correspond to a piece of data. So for example, this decoration meaning the finite singularities. And this weight function tells you the order of the singularity, the zeros or simple pole. And then the puncture corresponds to double pole. And for high order pole, we want to replace it with a boundary component and mark some point on this boundary component corresponding to the distinguished direction. So for example, for this order 4 pole, we'll replace this with a boundary component and mark these 2 points corresponding to these 2 distinguished directions. So basically, then this topological surface with boundaries and marked points and the decorations and punctures inside records all the information we have for the numerical data. So, for example, if we have a order 3 polynomial. Yeah, so yeah, the decoration and the puncture are and the boundary components, they are all singularity. And just decoration are finite singularity, and usually you need to put a weight to indicate the order. And the puncture will be double pole, and the high order pole will be boundary components, where the order will indicate by the number of marked points. So if you take a cubic polynomial to give you a global quadratic differential on CP1, then the numerical data is 3 simple 0 and 1 order 7 pole at infinity. So you replace the infinity with a pentagon, with a boundary component with 5 marked points. And you want to put 3 decoration inside, correspond to this 3 simple 0. And this pentagon with 3 points inside is the topological surface to record all the data. And for the other case we saw before, then we will have a diagonal with 4 decoration, and this is red ones, and we have 2 double pole. So we just draw 2 punctures, where I use the symbol sum to represent the puncture. Oh, this pentagon just this boundary with 5 marked points tells you that there's order 7 pole. And yeah, the 3 red decoration tells you there are 3 simple 0. So that's all the data you need. The topological. So doesn't matter it's pentagon, straight line, or ellipse. I just draw it to make it more beautiful. Yeah, it's a tugon. Yeah. Okay, so usually dynamical system people will just study the moduli space without any framing. So any such data up to symmetry, they will consider as the same point in the moduli space. However, we want to use this tetramural framing to make a covering for the unframed model space. So the actual data is we have this topological surface. So we take a homomorphism to the real block of the Riemann surface with respect to the quadratic differential. So as I said, that all the decorations, punctures, boundary record all the information. So here you are just forgetting about the complex structure on the Riemann surface and only use topological data to identify with this surface. So after you add this framing, then you have this framed model space, which is a covering for that for the unframed version, differ by the symmetry of the surface, which is the mapping class group. So the mapping class group here needs to preserve the set of decoration, the set of puncture, and the set of marked points, point-wise, set-wise. Yeah, so you just match the type of singularity to the type of singularity. And for this talk, we will study only the simple zero case, which is also known as the top strata in the union of all moduli space of quadratic differential on a fixed Riemann surface. And in this case, the number of zeros is given by this Riemann-Hurwitz formula. So basically, the information of the polar information will tell you how many singularity you simple zero you want to have. So sometimes we can omit this set of simple zero because we know the number, and that's the only thing you need to recall. And in this special case, so previously we are using the whole data to frame, which is called this Tetramuller framing. But then because the simple zero, the number, we know that. So we can also forget about that, just use the surface with punctures and marked points on the boundary to record the information. So this partial framing will give you a covering in between. And because you are using this unmarked surface to frame, so the covering group is the symmetry of this smaller surface. And the difference is the so-called surface braid group. So it is the symmetry group of the decorated surface to the undecorated surface. And then you just have this forgetting map, forget about the decorations. And yeah, later we will also mention that this is basically the fundamental group of the configuration space, where the simple zero you consider as a configuration on the undecorated surface. And in the case one, S is a disk without puncture. This is the braid group, classical braid group. And moreover, after we have this model space, we want to do some partial compactification. And at this point, maybe it's a bit weird, but later I will provide a couple of motivations. So first, we want to take a partition of the set of puncture, which I denote by left and right moon, maybe also called waning and waxing. And we will allow the collision of simple zero in this decoration set with the double poles in the right moon. So the partial compactification basically means that you want to add other type of singularity of quadratic differential. So usually you can just collide singularities. So this is the type of collision we allow. So basically, originally we only consider the simple zero for the finite singularity. Now we can also have simple pole, which is obtained by put some simple zero together with double pole and produce some simple pole. So after you choose this partition, we can take many strata and put them together. So as I mentioned, without the collision, if you only have simple 0, we have the top strata, meaning that the dimension of the moduli space is maximal among all these strata. So you are just adding low dimensional things kind of on the boundary, but later we will see it's not really on the boundary, it's filling some hole or filling some hyperplane. Yeah, so that's kind of the operation we want to have. And we want to do one more weird thing, is that for the puncture in this right moon, we want to give it Z2 symmetry, which I call yin-yang. So, you know, this is the Chinese terminology for Z2 symmetry thousands of years ago. And we do that, I mean, the idea behind this is that we're actually choosing a residue at a double pole. So if you have single pole, you lose this Z2 symmetry. But another way to say this is that when you add this partial compactification, so you add some extra strata, you want to do some Z2 orbifolding. Again, this seems a little bit weird, but later I will tell you why we want to do that. Yeah, so let's just review this running example. We start with this moduli space, which have 4 simple 0, 2 double pole, and 1 order 4 pole at infinity on CP1. So if you allowed one of the puncture to be collide, and then you want to add another strata like this. So you have 1 less simple 0, 1 less double pole, but you have 1 extra simple pole. And usually we want to do a Z2 orbifolding for this extra strata. And if you allow the collision of both of the puncture, then you want to add 1 more stratum with Z2 to the 2 orbifolding. Yeah, so that's all the moduli space we want to study, and we want to calculate the fundamental group of all of them. Yeah. So just a quick word is that after you choose this partition and maybe add this Z2 symmetry to make this yin-yang, so the symmetry of the surface will change a little bit, but not so much. So this is a technical point. Okay, let me give you some motivation of why we are doing this weird thing. Yeah, let's quickly go through this page. Basically, in representation theory of algebra, there's a machine which can produce an n-calabial category starting from any digit algebra. And in our setting, which is originally coming from cluster story, is that you have a quiver's potential. So a quiver is just an oriented diagram, and the potential is the sum of some cycles in the quiver. So for example, you can have this 3-cycle quiver with a potential A1, A2, A3. And the procedure to produce the calabial category is that you want to double the quiver. So you have sort of symmetry which corresponds to the calabial property in the category, basically meaning that between any 2 objects, if you have a home from X to Y or from 1 to 2, you should have another home from 2 to 1 with some shift. So this is why you have this double arrow construction. And the potential tells you how to define the differential of this path algebra associated with this graded quiver. So yeah, if you are familiar with this construction, that's standard things to do in cluster theory or representation theory of algebra. But what is the point? The point is that we have this piece of combinatorics here. So when you have this marked surface with punctures, so at this stage, we don't need the decoration. So for example, you can have a hexagon, or a pentagon with one puncture, then you can talk about the triangulation of it. So basically, you just connect the some marked points or the puncture and divide the surface into triangles. And of course, you have triangle. This is because later we want to put each decoration in a triangle, because we have seen that the foliation at simple zero corresponds to this trivalent structure. So this triangulation corresponds to simple zero. Anyway, after you have the triangulation, you can produce this quiver whose vertices are the arcs in the triangulation and whose arrows correspond to the angles of the triangle in this triangulation. Arrows are, so in each triangle, you just draw 3 cycles. So that's the most easy thing to do. Can you change all the orientation by opening ones? No. Orientation is fixed, which compatible with the orientation of the surface. So in each triangle, you will have a, say, clockwise. Yeah. Yes, of course, yes. So in each triangle, you have a clockwise 3 cycle, and around each puncture, you will have anti-clockwise cycle. Yeah, because in each triangle is clockwise, here is anti-clockwise. And then, so that is quiver. And for the potential, usually in cluster theory, what you do is that you take the sum of all 3 cycles correspond to triangle and minus all the anti-clockwise cycle along punctures. So that's the kind of the right way or the correct thing to do in cluster theory, because then the potential or the quiver potential has nice property corresponding to mutation in cluster theory. However, for us, we want to do something funny, because we have this partition of the puncture, and for the potential, we want to only minus the these cycles around punctures in the right moon. So we have many choices to do this, and these partitions, all the partitions we can have, then we will have many ways to produce this quiver potential, and then we can use the machine from homological algebra to produce this 3 Cabell category. And basically, this potential corresponds to some elements in certain Hauss homology, which this family of 3 Cabell category are a family of deformations. Okay, so we have this 3 Cabell category, and for each triangular category, we can define a complex manifold introduced by Bridgeland using the data of central charge and the T structures to produce this complex manifold. Yeah, so this is a nanomachinery whose motivation coming from the high stability from mathematical physics, but now is very popular because it relates to many things. So, for instance, in our case, so this space of stability condition is a homological invariant associated to each triangular category, and this provides a categorification of the moduli space we mentioned before. So if we start with this surface, and previously we say we have this moduli space with partial compactification and orbifolding, blah blah blah. And now I'm telling you that this moduli space, complex manifold, can be constructed homologically from this 3 Cabell category using space of stability condition. So this direction, the original seminal work was due to Bridge and Smith in the case that they want to allow the collision to any puncture, because they need to use the cluster theory to prove this result. And recently, in a joint work with Merlin Kreis and Fabian Hayden, we do the other extreme, that we do not allow any collision. So we construct a different three-carbon category to realize this model space. And now, so in this work, basically,
Just to clarify, but quadratic differentials are without instability. You consider all of them.
A strata. So I fix singularities.
So strata requires some stability, right?
So to define this quadratic differential, you just have the Riemann surface and the numerical data. And I'm telling you that from this data, there's another way to construct the model space of quadratic differential. No. Each element in the F chord corresponds to a stability condition on the triangular category. So that's the identification between these two complex manifolds. But the stability condition, to construct that, you only use homological data, like the triangular category and homological algebra, without using any complex structure or analysis. Yeah. 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 The theorem is stability space can be identified with model space of quadratic differential. Yes. So the correspondence is the foliation structure we are talking about on quadratic differential or Riemann surfaces correspond to slicing or T structures on category. The period map, which is the local coordinate for model space of quadratic differential, correspond to central charge on the category. And in the category, you have this atrium filtration for each object, and that corresponds to broken geodesic. So there's a dictionary between quadratic differential and stability condition. Yeah, so this is this is actually the byproduct of the paper. Yeah, but let's look at the example. So if we take this stratum we mentioned before, then we can construct this three-carbon category by taking the potential to be the sum of 2-3 cycles in this quiver, this purple quiver. Then the corresponding space of stability condition on this category will give you this model space. But later we want to partially compactify by adding another strata with orbifolding to this main strata. Then after you add that strata, this bigger space will realized by this model space of stability condition, where we modify the category by deform the potential a little bit, and this continues. Yeah, so basically, in previously, we construct many model space with possible partial compactification and orbifolding, and now on the homological algebra side, we construct many three-carbon categories to realize all of them. So in some sense, that is my motivation to do this orbifolding when you do partial compactification. Yeah. Okay, so now let's talk about the main result is that we want to calculate the fundamental group of these model spaces. So maybe I want to mention that like many years ago, Kontsevich and Zorich, they starting to calculate the connected components of model space of abelian differential. And later there were many works on this direction. Yeah, because understanding the topology of model spaces is important from dynamical system or geometrical topology, but somehow the calculating pi 1 or even higher homotopy groups is much harder. Yeah. So this is our attempt. So first, let's talk about some maps. The first map is when you have a quadratic differential, you can forget about the complex structure and then map to this Riemann surface. But you need to remember all the infinite singularities, but consider finite singularity as configuration. And then you can have this Abel-Jacobi map from this Riemann surface with markings and configurations to this Picard variety, which is just some torus. So here we are taking the higher order pole, consider that as a divisor to construct this map. So this map, there are many choices because you can forget about certain poles.
One last question. So, generalized Picard equal, generalized Picard variety, right? Big with W. What is big with W? Just generalized equal.
Yeah. This is just. Yeah, this is just the torus. Yeah. And then if we combine these two maps and take the pi 1, then we get the pi 1 of the moduli space. So here we are mainly focused on the principal strata. Yeah, because once we know how to calculate the pi 1 of this, we know how to calculate the other ones. And then the first map is mapped to pi 1 of this configuration space, which is the surface Bragg group, which I will talk about in more details later. And for this torus, we have the first homology of the surface. So here, I secretly forget all the punctures. So that's kind of the key. And the main theorem says that this is actually a Chauvet sequence. So this AJ map was considered by like Walker and others from other community, and it is not that hard to describe the image of this map as the kernel. And yeah, this AJ map is obviously surjective. So the hard part is to show this map, which is also known as the monodromy map, is injective. But once we know this is the kernel of the AJ map, we also understand the topology of the covering space. So what is the point? The point is that originally we have this tetramural frame in the moduli space, which is a big covering space. However, it is not connected. So this Chauvet sequence tells us that the number of kinetic components here is parameterized by the first homology of S, forgetting about the decoration and the puncture. And moreover, each of the kinetic component here is simply connected. So this basically tells you all the information of pi 0 and pi 1. And yeah, later I will mention that conjecturally, this will determine its homotopy type. So basically, this space should be contractible. Anyway, so here we are talking about the framed version, and if you want to take the moduli space without framing, and this is also the kernel of some extended AJ map, where you want to take the starting from mapping class group instead of the surface Bragg group. Yeah, so let's dig in to see what is really this Abel-Jacobi map. So topologically, this is very easy. When you take an element of the surface Bragg group, so basically you are moving around the decorations on the surface. So there are many simple zero or decoration. You just move it around. And as a set, it needs to come back to itself. So if you take the path of all of them, connect all of them, it will give you many loops on the surface. But then you need to forget about the decorations because they're moving around. So this will give you a map to H1. So you cannot map to pi 1, but to H1 is fine. So that is the map. But the most natural thing here is that you're still remembering the puncture. But the point is that after we choose the partial, partition, we can forget about part of the puncture. But in the main theorem, we forget all of them. Yeah. But for the partial compactification case, we want to forget part of the punctures. So this is the AJ map. Yeah, in the theorem, we are forgetting about all the punctures, which we will just denote by AJ. And another thing is that what are the generators of the surface braid group? And there are just two types. The first is that if you take a path connecting to decoration, you take a neighborhood, which is a disk, then you can do this twist known as braid twist along this arc. If you take the branch double cover of this disk branching at these two decoration, you get an annulus, and this arc becomes a simple closed curve in the annulus, and this braid twist leads to a Dan twist. So maybe you are more familiar with that. And this is also known as the half Dan twist. So this is the first symmetry on the surface. And the other symmetry on the surface is that it's called this point pushing diffeomorphism, is that you drag a decoration along a loop on the surface and twist along that loop like that. So this will equal to the Dan twist along the inner and outer boundary in this neighborhood of this loop. So this is the two generator of the surface braid group. And to understand the kernel of the AJ map, we want to introduce this mixed twist group. So the first part of this group is the braid twist group, generated by all the braid twists along any arc, simple arc, connecting to decoration. And the other part is you want to take a decoration and go around a puncture in the left moon. Yeah. So that's this mixed twist group. So depending on how many puncture you allow to collide, or depending on the partition, you can make many intermediate groups between the smallest one, the braid twist group, and the biggest one, the mixed twist group. So there are many things in between. All of them are normal subgroup of the surface braid group. And the theorem says that the kernel of the AJ map is precisely the mixed twist group, where if you want to map to this surface with right moon, where you forget about the left moon, then the left moon appear in the kernel, so in the generator of the mixed twist group. And the whole surface braid group consists of these parts. So the braid twist group and this H1 of S are you take a decoration, go around a boundary component or a genus of this surface. And the other part, you go around the puncture. So in the main theorem, we're using this group. And so what's the point and why this mixed twist group, which is the kernel of AJ map, equals the pi 1 of the moduli space of quadratic differential? So next, let me tell you the geometric meaning of braid twist and L twist from quadratic differential point of view. So the first is the braid twist. So originally, we don't have this foliation. We just have this octagon, like this disk, which is the neighborhood of an arc, this red arc. So this arc in quadratic differential, this is basically connecting two simple zero, and in the moduli space, we can actually collide these two simple zero to get a double zero. However, if you collide these two simple zero to a double zero, like in the middle picture, then this point is not in the top stratum we are considering because we are not allowed the double zero. However, you can just twist this two zero, just move it around, like say around this loop. It will be rotate clockwise, and it will come back to itself. So this is the loop in the moduli space of quadratic differential. Yeah, if you forget about the foliation structure, everything, it becomes the braid twist we're drawing here. So that's the meaning of braid twist in the moduli space of quadratic differential. So for those people who are familiar with mutation in the cluster theory or Donaldson-Thompson theory, for each triangulation, it corresponds to an abelian category or a heart in the 3-carbonyl category. And then you have this Donaldson-Thompson invariant. And from here to here, this corresponds to a flip of triangulation or all crossing. I think this also appeared in yesterday's talk. So there are some link there, but I will not say more on that direction. So for the L twist, or this point pushing, it corresponds to a collision between simple zero, this one, to the double pole. So again, if you collide these two to get a simple zero, this point is in the partial compactification, but not in the top stratum with only simple zero. And similar to the previous case, you can move these two around, but this time I will just fix the position of the double pole and move the zero around it. And the foliation structure changes dramatically, involves this logarithm spiral. But anyway, so this is the other monodromy in the moduli space. And again, this also corresponds to some wall crossing, if you know what I'm talking about.
One more very good question. So this is what happened upon the mutations, right?
Yeah.
Right?
Yes.
This corresponds to the previous picture, right?
Yeah. So here, so if you take the, later I will talk about the triangulations and mutation of leap, but it's basically you take the homotopy class of generic trajectory, you will get the WKB triangulation, and that. Yeah. So on the top and on the bottom are the ones which you have saddle connection, which you do not have a triangulation, but that's the wall crossing where it happens. Yeah. Okay. So after we understand that, we can extend our main result to the partial compactification. Because what is the point? The point is that we allow the simple zero collide with double pole, which we fill in this point in this loop. So in fundamental group, we're killing this loop. But this is really a two-dimensional picture I'm showing you. But the real picture is that you have this, say, n-dimensional convex manifold. And the middle picture corresponds to complex codimensional one hyperplane you are filling. And project to the plane, you're filling a point in a loop. So in fundamental group, you are killing the L twist around the right moon. And if you want to do orbifolding, which we really want to do, then you want to taking out the square of the loop. Again, let's see some examples. So in the running example, if you calculate the pi1 of this diagonal with 2 puncture, usually you get this braid group of type affine type 4, affine type C. And if you do partial compactification with respect to P2, you get affine type B. And if you allow collision to both of them, you get type D, affine type D. So yeah, maybe I draw one more picture. Is that so we are choosing a triangulation, and then the red one are the due of the triangulation, which so for each this red one you correspond to a braid twist. For each of this loop correspond to an L twist. But then this will give you a type C braid group of this configuration. So this 4 means that the braid relation is ABAB equals BABA. Yeah, and this one I draw the triangulation so that it looks like an O, if you can see. Then we can mutate a little bit. Then we can, if we allow this, we put this puncture and becomes yin-yang, and we get this type B, affine type B. And then if we mutate one more time, we get a fox, which corresponds to affine type D. Yeah, so that's basically the idea. So this also justify that why we want to do take some of the puncture to become yin-yang, so that we can really produce all the non-exceptional Euclidean arcing braid group. In particular, type B, you want to have this one puncture and one yin-yang to match the affine type B configuration. Yeah. Yeah. So just a quick remark is that if you are familiar with cluster theory or Brujan-Smith, that the Z2 symmetry really play a key role. Where somehow here we have a topological understanding of this Z2 to the number of yin-yang, which is you have this lattice and you quotient the image of the Abel-Jacobi map. Yeah, but let me just quickly go through here. So finally, let me show you more pictures and tell you what is the idea of the proof. Is that you just need to forget about the foliation and only remember the triangulation structure. So usually when you have a triangulation, you have flip, which is you replace the diagonal in the neighborhood, which is a square usually. But you can also have decoration to flip. Then the flip will have orientation. And for the self-folding triangle, usually people say you cannot flip at this edge, but you can if you have decoration. And the covering is the forgettable map. So if you have a triangle with one puncture, this is the naive flip graph people usually draw, where each vertex is a triangulation, each edge is a flip. But the correct thing to do is you want to double each edge in the previous graph, because the flip should have orientation. And you want to add all the loops corresponding to flipping the self-folded triangle, which, I mean, it becomes itself, but it makes sense. So this is the right thing to do. In cluster theory, what they do is that they want to take 2 copies of the previous exchange graph and glue them together to get an association. So for us, we want to mix up these 2 operations. So for this one is for the puncture, for this one is for the yin-yang. And then we can construct this flip graph of triangulation, decorated or not. And the point is that they are the skeleton of the moduli space. So this is a technical result, but the point is that each triangulation corresponds to a top-dimensional cell in the moduli space, and each flip corresponds to a co-dimensional one wall between them, and that's the wall crossing. But yeah, this is a skeleton, so we have a surjective map from pi 1 to pi 1, and then we want to understand the kernel of this map. So what is that? So these are this type of relation. For the square and pentagon relation, it is well known. And the point is that after you add decoration, the pentagon, for example, will have this 2-step equals 3-step relation, which corresponds to the famous pentagon identity for logarithm. And in previous paper, Alice and I also found this hexagon relation, which is also important, but this is without puncture. With puncture, 2 more relations we want to add. So notice that I put the decoration in weird places. Square and pentagon and hexagon, so these 3 are all appear in cluster theory. But these 2 are a little bit new. But what is the point? The point is that after we add all the relation, the map from the exchange graph with relations, which becomes 2-dimensional setup complex or group poise, will give you the fundamental group of the moduli space. So, and finally, let me show you 2 more pictures. The first one is that the braid relation. So when you have braid twist, you have this 2-step of flip of triangulation correspond to 1 braid twist. Then you have ABA equals BAB. So this braid relation decomposed into 5 or 6 pentagon relation. So this picture was known to topologists, for example, Kramer, but I think he didn't draw this beautiful picture with decoration. So I draw something. And for the puncture case, we can draw this picture decomposing. So this S is L twist. This U square is braid twist. So you have SU square equals U square S U square S. So this higher braid relation decomposed into 4 hexagon relation, which is, I think, the highlight of the proof. Although, I mean, this is the easy part. Yeah, so let me stop here. Yeah.
Any more questions? Initial question. What are implications to modular spaces of curves? What is differentiation? The directory?
What differential?
Modular spaces of curves themselves. Today's differentials are actually very helpful in our development.
I don't know. Yeah, I mean, for me, one of the things I don't mention in full detail is that I want to attack this K-1 conjecture. And this is equivalent to the contrariability conjecture for space of stability condition. And also, the Donaldson-Thompson invariant I mentioned is kind of local. I mean, the existence of Donaldson-Thompson invariant is the local simply connected list. Yeah, and so I want to do the global version. Yeah.
Any other questions?
So as you mentioned that the mic is not what I can talk about. You mentioned that the pentagon equation corresponds to the identity of the logarithm.
Yes.
Does the hexagon relation correspond?
I think this hexagon relation corresponds to some quantum diagonalism identity, and it also corresponds to some wall crossing phenomena. So that's in the very recent work of Kidwa and Williams. Yeah, basically in the Bridge-Smith story, they also studied this Johnson-Thompson invariant. So in that case, you can use Bridge and stability condition to write DT invariant as a product of quantum diagram. And the square and pentagon tells you that the different stability condition gives you different way to calculate that invariant. But in the puncture case, you also need a hexagon relation to realize that different stability condition gives you different products, but that will give you this identity. Yeah.
Other questions? May I ask, so in your talk, I mean, in your constructions, do you have any restrictions on the genus of the curve?
No.
And, so it can be non-compact, it can be disk.
Yeah. So basically, when we realize the braid groups, that's always genus 0 with at most 2 puncture. So that's the classical arting Euclidean or spherical arting group people study. But for the higher case, so basically we have a class of generalization for this type of arting braid group, which topologists didn't study before.
Thank you very much. If there are no any other questions, let's thank the speaker again.
Yeah, thank you.